Hello friends, in today's question, a uniform thin cylinder disc of mass m and radius r is attached to two identical massless springs of spring constant k, which are fixed to the wall as shown in the figure. The springs are attached to the axle of the disc diametrically on either side at a distance d from its center. The axle is massless and both springs and the axle are in horizontal plane. The unstretched length of the spring is L. The disc is initially at its equilibrium position with its center of mass at distance L from the wall. The disc rolls without slipping with the velocity v0, which is given as v0 in I, it means in x direction. The coefficient of friction is mu. So we have these four questions that are based on this particular problem. So in the first part, A part, the net external force acting on the disc when its center of mass is at displacement x with respect to its equilibrium position. So it means this center of mass, or we can say the equilibrium position is this position, and now it is being displaced by a distance x in this way. So both the spring will be extended by the same amount, and now the disc will be somewhere here. So we can draw this diagram a little bit simpler. So because of as the spring are both displaced by the same amount, that is x, so therefore the force which will be acting because of the spring will be 2kx, and it is given that there is a v0 velocity of center of mass along the x direction, and because of this the spring force, this particular disc will be forced to move in the backward direction. Okay, so because of that there will be frictional force Fr, which will be acting opposite to the direction of this spring force, or we can say there will be a linear acceleration of A in the direction of the spring, and because of this frictional force, a torque will be acting on the disc and it will be resulting in an angular acceleration. Let us call that alpha. So this is a basic, you can say, simplest form of the disc under when it is displaced by, when the spring is rather displaced by a amount x. So we can say that, let us try to solve part A. So in part A, it is given the spring, or we can say the springs are displaced x from its mean position, Therefore the net restoring force, or we can say spring force, therefore net spring force on the disc, let us suppose that is given as Fs, which will be equal to 2kx, and it is said that the disc is going to roll, it means without slipping. So we can say for pure rolling, linear acceleration will be equal to r times angular acceleration. Now from the figure, we can see that the spring force is opposite to the, you can say, the linear velocity, that is v0. can say the spring force Fs is opposite to V naught. Therefore, the disk accelerate with acceleration, let us suppose that is given as A, and the frictional force acts opposite to spring force resulting in angular acceleration which is given as alpha. So therefore we can write the equation for the linear acceleration, that is A. We can say for linear acceleration A, can write that ma will be equal to spring force minus the frictional force. So from here we can say our A is equal to spring force Fs is given as 2kx, so this will be 2kx minus frictional force divided by m, and there will be torque produced by the frictional force. Okay, a torque will be produced by the frictional force which is given as tau. So we can write that tau is equal to R cross frictional force, and which will be also equal to moment of inertia of the disk multiplied by angular acceleration alpha. And moment of inertia of the disk, we know that I disk is given as half mr square. Therefore we can write that R frictional force will be equal to half mr square multiplied by angular acceleration alpha. R cancel with this square, so from here we can write that our alpha will be equal to twice into frictional force divided by mass into radius. So this is the value of the angular acceleration, and as the motion is pure rolling, so we know that for pure rolling A is equal to R alpha. So substituting value of A as well as R in this equation, A is governed by as 2kx divided by m minus Fr divided by m, sorry it is capital M, is equal to, and we have R, and this gives us alpha is 2 multiplied by frictional force divided by mass into radius. And radius cancels out. So this becomes equal to 2Fr divided by m. And here m also cancels out entirely. Let me do it here. So this m goes away. So we are left with 2kx minus fr is equal to 2fr. So which gives us 2kx is equal to 3fr. So from here we can find out the equation for the frictional force, that is Fr is equal to 2 by 3 k multiplied by x. This is the equation for the frictional force. And now we can find out the net force acting on the disc. You can say net force acting on the disc. Let us suppose that is given as F net, and F net will be equal to the spring force minus the frictional force. Okay, so spring force is Fs, frictional force is Fr. Fs is our 2kx, and frictional force we just found out is 2 by 3 kx. So from here we get that F net is equal to, this becomes 6 and 2, that is 4 by 3 kx. But we can see that the net force is opposite to the velocity. Okay. From the figure, or we can understand from here that net force is opposite to the velocity. You can say, but F net is opposite to the velocity v naught. Therefore, we can write that F net will be equal to minus 4 by 3 kx. Okay, so we got the net force. So if you say option number for question number A, option number D is the correct option. So we can say option D is correct. Now let us go for B part. In B part, we are supposed to find out the angular velocity omega if the disk undergoes a simple harmonic motion. For B part, from here itself, we can say that F net will be equal to, F net is equal to mass into acceleration, which is equal to minus 4 by 3 kx. Or we can say that our acceleration A is equal to minus 4 by 3. This becomes k upon m multiplied by x, which can be written as 4k 3m multiplied by minus of x. So from this equation, we can say the acceleration is negative of x, which means a simple harmonic motion. Therefore, we can write that the angular velocity omega, angular velocity omega square will be equal to 4k divided by 3m, and which comes omega is equal to square root of 4k divided by 3m. So for the option available, we can say option number D is the correct option. We can say option D is correct. And the C part, maximum value of V naught, for which the disk rolls without slipping. So C part, so for pure rolling we can use the conservation of energy. So we can say conservation of energy. So it means the disk is going to have two energies. One will be rotational, another will be translational, and that will be their sum will be equal to energy because of the spring. So you can say disk energy will be equal to spring energy, and disk energy we can say will be translational energy plus rotational energy, and that will be equal to spring energy. And we substitute the formulas, we get velocity is V naught, so we get half m V naught square plus half moment of inertia of the disk, which is I disk, and the angular velocity omega square will be equal to twice into half k x square. Okay, spring energy means for both. Okay, we have spring energy into 2, and here also spring energy into 2 because we have two springs. Therefore, substituting value of I disk, which is half mr square, so we get this as 1 by 2 m V naught square plus half, we get half mr square, and omega square we just calculated, or omega square we can put in terms of the V naught, okay, and that will be V naught square upon r square. This will be equal to, and 2 cancel with 2, so we get this as kx square. Here r square goes with r square, and rest are same, so we get half m V naught square plus this will be 1 by 4 m V naught square is equal to kx square. So we can solve it taking m V naught square as common. So we get m V naught square as common, and we get 1 by 2 plus 1 by 4 is equal to kx square, and this will be equal to m V naught square, 4 we over LCM, so this becomes 2 plus 1 is equal to kx square, and we get m V naught square multiplied by 3 by 4 is equal to kx square. So it says that the maximum value of V naught when we have without slipping. So you can say for maximum, you can say x was given as 1 second displacement. So you can say for x is equal to x max, we can write this equation as x max square will be equal to, this becomes 3m divided by 4k multiplied by V naught square, so which gives us x max is equal to, we have square root of 3m divided by 4k into V naught. So this is the maximum extension, and we are supposed to find out the maximum velocity. So we know that the value of the friction, we just calculated, the frictional force will be equal to Fr, and that we calculated is 2kx upon 3. So if x is equal to x maximum, the frictional force can be written as Fr max. So we say Fr max is equal to 2k by 3, and this becomes x max. So substituting value of x max, we get 2k by 3, and we have this as 3m upon 4k multiplied by V naught. And the maximum value of the friction, Fr max, will be equal to nothing mu mg. So equating them, we get mu mg is equal to 2k by 3 square root of 3m divided by 4k and V naught. Now it is simple solution, and we can say that let us solve this under the square bracket, taking inside, so this becomes 3m multiplied by k square multiplied by 4 divided by 9 multiplied by 4k, and this becomes V naught. This k cancel this square, 4 gives with 4, and 3 cancel with this 3. Therefore, we are left with this is equal to, we have mk divided by 3, and this becomes V naught, and this is equal to mu mg. Now a simple left to right shifting, so we get V naught will be equal to mu mg, and this square root, this becomes 3m times k. I am taking m inside the bracket square root, so this becomes mu g, and we have 3 into m square divided by mk, and m goes with this square, so we are left with that V naught will be equal to mu g multiplied by 3m divided by k. So this is the maximum velocity without slipping. Okay, and if we see the option available to us, we can say in that option number C is the correct one. Okay, you can say option C is correct. Option C is correct. This question is complete, but there was a similar question that was asked in one of the papers, and one second, yeah, and there it was given that we do not have two springs, neither we have a disc, we have a some kind of roller, and let me draw the figure. So this is a cylinder, and this cylinder is connected, this is the axial point, and this is connected to a single spring like this, and this is connected to a wall. And we have, you can say it is something like this. The spring constant is given as K and the radius is given as capital R, and the same things was asked here also. Okay, we have to find out the velocity, we have to find out the angular velocity, and we have to find out another parameter was that we have to find out the third thing. Forgot the third thing. Yeah, here it is. We have to find out the maximum velocity, angular velocity, as well as the net external force acting on the disk. Okay. So here also the only difference is that instead of two springs, this has only one spring, and here also it is displaced by the amount x. Sorry, I missed it. So this is the basic cylinder having radius r, and it is connected by a single spring to a wall, and here also it is being displaced by the amount x. Everything is same, all the three things asked are same, but here is only consisting of only one spring. Okay. And the figure which we can draw similar to the previous one will be something like this. So there will be a force of kx because it is consisting of only one spring, and it will be resulting in the acceleration of A, and we are going to have a frictional force Fr, and we have a angular acceleration that is alpha. In the first question it was 2 because there were two springs. Here the only thing is that it consists of only kx. Okay. And in this case there is, you can say, another method to find out your angular velocity. And for find out the angular velocity, you can say a theorem of parallel axis is being used. Okay, rest things are same. So let me solve it for only angular velocity. So we can say for angular velocity, here the theorem of parallel axis is being used to find out the angular velocity. And for that, let me write for theorem for angular velocity, theorem of parallel axis is used. So we can write that the frictional force is acting at the point of contact, so this is going to generate a torque. Okay. Therefore we can say torque due to frictional force is being applied at the bottom, that is at point of contact. Whereas the force due to spring is being applied at center of mass. Whereas force due to spring is being applied at center of mass. Therefore, we are going to use theorem of parallel axis. Therefore, theorem of parallel axis, and which gives us that moment of inertia I prime will be equal to moment of inertia about, you can say, disk plus the shifting distance, that is r square, and multiply by the mass. So this is the shifted moment of inertia from center of mass by a distance r and having mass m, and distance is r square, r and taking the square. Therefore we get that I prime will be equal to I disk is half mr square, and this is also equal to mr square. So we get this as 3/2 mr square. Now the torque will be given as I prime multiplied by alpha, or it will be also given as r multiplied by f, where F is your spring force, rather say Fs. So substituting the value, we get this as 3/2 mr square multiplied by alpha is equal to r and minus kx. So we can write this as 3/2 mr square plus, not plus but multiply, and this is our angular acceleration, so we can say it as a double derivative of displacement, and divided by r is equal to r minus kx. So this r square goes with these two r. So from here we get that double derivative of x will be equal to minus 2/3, and here we have kx, and this is m multiplied by x, and double derivative of x is nothing but acceleration. So therefore we get a is equal to, this will be equal to 2/3 km and minus of x. So therefore from this equation we can say that our linear acceleration a is directly proportional to minus of x, which is nothing but shm. Therefore omega square is equal to 2/3 k upon m, or we can say angular velocity is equal to 2k upon 3m. Okay, so we can use theorem of parallel axis to find out the angular velocity. Okay, so these two are, you can say, different examples, but the basic approach is same. Okay, in the previous case, which was our original question, they were having two springs, but in this case there is only one spring. That's the one major difference, and rest of the thing will be, the solution will be same. Okay, so this is some kind of, you can say, question based on similar principle. Question based on similar concept. The only thing that differentiate here, I have used theorem of parallel axis to find out the angular velocity, and in order to find out external force we are going to use same formula. In order to find out the maximum value of V0, we are once again used to use the same thing. Only difference is we are going to, I missed here square root. So this completes finally the questions. Thank you.